All right, so welcome to Math 389 eventually. So what I want to do today is I want to talk about moments in random matrix theory. And so the challenge is, how do we compute some of these quantities? All right, so we were talking about Catalan numbers before. There is a lot of different ways to do these calculations. I've got a couple of links over here. Some of them are talking at a very high level about what's going on. If you're interested in calculations like this, they're good to look at. Some of the calculations are pretty straightforward, while other ones become a little bit involved to rigorously show that they go to what you want. There's a lot of different statistics you can look at. Right now, we're looking at, for the most part, just trying to count the number of normalized eigenvalues in an interval. And that's where we're going to get the semicircle law. And we're going to try to show that what matters is having things matched in pairs with non-crossing matchings. So the to-do list for today is a little bit long. So we want to calculate the moments of the standard normal. So has everybody seen the standard normal before? Okay, good. Then we want to calculate the moments of the semicircle. Then we want to show that the odd moments vanish in the limit of the semicircle, and that's easy. And then the odd moments vanish in the limit of the random matrix ensembles we're looking at. Then we want to count how many ways are there to match things in pairs. And we're going to see that that's the Catalan number. So it's going to be a slightly different definition of the Catalan numbers than we've seen before. Not a big deal. Then we're going to evaluate the contribution of these non-crossing matchings. And we're going to show that it equals the moments of the semicircle. And then I'm going to wave my hands a little bit about the non-crossing ones. Okay. And so hopefully we will fix all the technology stuff, or if this room is just available, this room actually has seats facing in the right direction. So we might just stay here. All right, so hopefully everybody has seen the normal distribution. Since you just arrived, you didn't technically answer that question, but I'm assuming you've seen the normal?
Yes.
Yes, all right. And so we want to calculate the moments. And so a lot of times, if you do a little bit of your change of variables, you can adjust so it has mean 0, variance 1, and then figure out how you rescale. So if you have variance 1, if you want to calculate the third moment, if you now have various sigma, you just rescale by a sigma cubed. And so how do we calculate the moments? Well, if we want to do, say, standard normal, the 2mth moment would be the integral from -infinity to infinity of x to the 2m, 1 over square root of 2 pi e to the negative x squared over 2 sigma squared dx. I'm not doing the odd moments of the standard normal because the odd moments is 0 because it's an odd function. So any thoughts as to how you would do this integration? Oops. I'm not doing the standard normal. It's actually easier to do it with mean 0 and variance sigma squared. So how would you do this integration? What technique would you use? So you've got an x to the 2m and an e to the negative x squared over 2 sigma squared. What technique would we use? Yeah, it's integrate by parts. And so another way we can do this is we can differentiate under the integral sign. So to differentiate under the integral sign, we need an identity. And so because this is a probability distribution, if I take m equals 0, that's just calculating the density, which would just be 1. So because it's a probability distribution, I can get 1 is equal to the integral from -infinity to infinity of 1 over square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx. Well, I can move the sigma squared over to the other side, and I get sigma squared. Oops, I've got a square root. So it's just sigma is equal to the integral from -infinity to infinity of 1 over square root of 2 pi e to the negative x squared over 2 sigma squared dx. And then, a tremendous amount of this class is operations, switching the orders, just boldly going forward. So what's the derivative of an integral? Just the derivative of the integral.
Oh, I mean, as in the integral is not involving.
No. I want to. I have this function which depends on sigma, and I integrate it, and I want to take the derivative with respect to sigma. What should I get when I take the? So what's our phrase? The derivative of an integral is the integral of the derivative. And then I just need to figure out what power of sigma do I want to multiply by to make things nice. So, we start off with this relation, and we're going to apply sigma to the a d by d sigma. I don't know what's a good power of sigma to multiply by. We'll figure it out very soon. And so if I come over here, so I apply sigma to the a d by d sigma. So the left-hand side just becomes sigma to the a, right? The right-hand side is sigma to the a, integral from minus infinity to infinity, 1 over square root of 2 pi. And now we have the derivative of the exponential. Well, that's just going to be the exponential again, e to the negative x squared over 2 sigma squared. And then we have the derivative of negative x squared sigma to the minus 2 dx. So we have sigma to the a, integral minus infinity to infinity, 1 over square root of 2 pi, e to the negative x squared over 2 sigma squared. Now we have the negative x squared sigma to the minus 2. When we take the derivative of sigma to the minus 2, we're going to get a negative 2 sigma to the minus 3. So the negative signs reinforce, and we'll get times 2 x squared sigma to the minus 3 dx. Notice that this is almost the second moment. This is the integral from minus infinity to infinity, x squared, right? I've got a factor of 2 outside. And then I've got a 1 over square root of 2 pi. I've got sigma to the a minus 3, e to the minus x squared over 2 sigma squared dx. What would I want a to equal? Not 3. And there's a small algebra error here, which, I'm sorry, it's x squared over 2. So the 2 cancels. I don't want a to be 3. We want it to be 1. Nope, not 1. You're getting closer. 3 was too high, 1 was too low, 2. So what we want to do is we want to take a equals 2. And then we would get sigma squared is the integral from minus infinity to infinity, x squared, 1 over square root of 2 pi, sigma to the minus 1, that becomes a sigma squared inside the square root, e to the minus x squared over 2 sigma squared dx. And now that's the second moment. That's just the expected value of x squared, the second moment. And that's also the variance as the expected value of x equals 0. So by differentiating under the integral sign, we can actually calculate the second moment. And so we just showed the second moment is sigma squared. Building on this success, what should we look at next? Fourth one. So we should apply sigma to the a d by d sigma more than once. So what we can do is we can try to come up with a recursive formula. So we start off with, sigma was equal to the integral from minus infinity to infinity of 1 over square root of 2 pi e to the negative x squared over 2 sigma squared dx. And so the question now becomes, what's the best thing to apply? And so if we want to apply something many times, when we take the derivative of x squared over 2 sigma squared, we're going to be getting a sigma to the minus 3 coming out. So if we're doing that, now what power of a would you like to take to get rid of that? To make things nice. Because we want to keep doing this many, many, many times. Because every time we do it, we get an x squared coming down. So we want an x to the 4th, we would do it twice. If we want an x to the 6th, we would do it 3 times. But we don't want to have to use the product rule by having all these sigmas come out. So what power of a would we like to take?
Which step?
3. So apply sigma cubed d by d sigma. And so now when we do it on the first time on the left-hand side, what do we get? We get sigma cubed times 1. And on the right-hand side, we get minus infinity to infinity, 1 over the square root of 2 pi, e to the minus x squared over 2 sigma squared. And now we take the derivative of that and multiply by sigma cubed. So we'll have sigma cubed, and then we'll have negative x squared over 2. The negative 2 is going to cancel, and we will get x squared sigma to the minus 3 dx. Oh, that's going to be nice. That's going to just give us an x squared. So we get sigma cubed times 1 is the integral from minus infinity to infinity of x squared, 1 over square root of 2 pi e to the negative x squared over 2 sigma squared dx. And if we wanted to get now the second moment, we just divide both sides by sigma. Now let's apply it again. So this was, sigma cubed d by d sigma. Let's apply it again, sigma cubed d by d sigma. So what do you get when you apply sigma cubed d by d sigma to sigma cubed? We'll get 3 sigma to the 5th, right? But I'm going to write it as sigma to the 5th times 3 times 1, because we had the times 1 from before. And now on the right-hand side, all we're going to do is we're going to just get an extra power of x squared. Let's keep doing this. Let's apply another sigma cubed d by d sigma. When you have sigma to the 5th, you're going to have a 5 come down. Sigma to the 4th times sigma cubed is sigma to the 7th. 5 times 3 times 1 is the integral minus infinity to infinity x to the 6th, 1 over square root of 2 pi e to the negative x squared over 2 sigma squared dx. And so if we ever wanted to calculate the 6th moment, we just divide both sides by sigma. If we want to calculate the 5th moment, we would divide the previous one by sigma. But by doing it like this, it makes all the subsequent integration very nice. If I want to calculate the 2mth moment, well, this is a 300 level class. So at this point, I think you can all see the pattern and prove it by induction. What would I get on the right-hand side? What would be the power of sigma? (2m plus 1). So let me put that extra power of that plus 1 on the other side. Let me move it over, right? We had we had sigma to the 2m plus 1. Oh, yeah, I'll do it slower. We have 2m plus 1, and now it's going to be what? 2m minus 1, 2m minus 3, ... 3 times 1. So this is the same as sigma 2m, 2m minus 1 double factorial equals the integral from minus infinity to infinity x to the 2m, 1 over square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx. So here, n factorial is n minus 1 all the way down to 1. n double factorial is n minus 2 dot 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 down to 4 times 2 if even, or 3 times 1 if odd. So the double factorial is every other term. It is not the factorial of the factorial. And again, you get to choose what you want to define. You could easily define the double factorial to be the factorial of the factorial. But that just doesn't arise combinatorially as often as the double factorial every other. And so we've just shown that the even moments of the Gaussian, well, the sigma is just rescaling. It's just sigma to the 2m times 2m minus 1 double factorial. What's nice is if you want to get the moments of the standard normal, this is the easiest way I know to do it. You calculate the moments for a more general normal distribution, and then you set sigma equals 1. This allows you to use differentiating identities. So it's a really wonderful technique. You have to justify interchanging the order of a derivative and an integral. That can be done. And I know some people are looking at that for one of their projects. When are you allowed to switch the order? You're in math, and we have to be very careful. In other departments, they're a little bit freer with that. And that can cause problems. You can't always do it. But here, the Gaussian is converging so rapidly, it's decaying so quickly, this is not an issue. Okay, so now we have the moments. Now, when you see something like 2m minus 1 double factorial, you should always ask, does this have any significance? So the double factorial and combinatorics. So imagine we have 2n people who want to match in n pairs of 2. How many ways? Anybody want to guess how many ways there are to match 2n people in pairs? Yeah, right. Foreshadowing, the art of a great lecture, right? Probably the double factorial is going to come into play. Now, what do you think the answer is?
I know the answer because that was great.
Right. So you've become mute. So n double factorial? So 2n double factorial is reasonable. You're off by 1. It's actually 2n minus 1 double factorial. You should have known that. And the reason you should have known that is on the previous page, when we were looking at the moments of the Gaussian, we had 2 minus 1 double factorial. And again, a lot of mathematics is pattern recognition. Seeing that this is coming here, probably a 2n minus 1 is going to come into play. There are lots of ways to prove this. Let's see if I can prove it correctly. For the first pair, how many ways can I choose who's in the first pair? Two and choose 2. How many ways can I choose the second pair? So 2n minus 2 choose 2, down to 4 choose 2, and 2 choose 2. Well, 2n choose 2 is 2n times 2n minus 1 over 2, and then 2n minus 2, 2n minus 3 over 2, dot, 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 4 times 3 over 2 times 2 times 1 over 2. This is 2n factorial over 2 to the n. That's not double factorial. I have made one of the most cardinal sins in combinatorics. Yes, how? Yes. So notice the words I'm using. First pair, second pair. If I just care about matching people in pairs, do I care if you're the first pair or the second pair? No. So how many ways are there to order n pairs? N factorial. So what do I have to divide by? And so I have to have a 1 over n factorial here. Now it becomes algebra. And so if I want to do it by algebra, I have 2n, 2n minus 2, 2n minus 4, dot, 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 4 times 2, which is the evens. And then I have 2n minus 1 double factorial, the odds. And then down below, I have 2 to the n and n factorial. Oh, that's nice. That gives me 2 to the n, 2 to the n minus 2, 2 to the n minus 4, dot, 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 4 times 2. Because the 2's bump up the n factorial to 2n double factorial. And so this is going to just give me 2n minus 1 double factorial. So that's one proof. Another proof, who would like to be special today? Okay, so you're special. We're going to do everything about you. Okay? So how many people are there in class? There are 2n people in class. Right? You are special. How many people can we match with you?
Only one person. I want 10 people match.
Well, no. You're not that special. You only get one person. All right. There's 2n people in class, and you can't be matched with yourself. There's 2n minus 1. So there's 2n minus 1 ways to match somebody with the first person. Now take anybody who's left. They've got to be matched with somebody. How many ways are there to match them? So you can either do it like that, 2n minus 3, 2n minus 5, dot, 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 3 times 1. Or if we call it maybe w sub 2n for the number of ways with 2n people, it's 2n minus 1 times the number of ways with 2n minus 2 people, and we have a recurrence. Once I match you with somebody, I now have 2n minus 2 people left over. And by induction, we know what that is. Or now this is a recurrence relation to solve. And you can easily see the factorials coming into play. So there's a really nice combinatorial meaning to 2n minus 1 double factorial. Whenever you see anything in mathematics that has a story behind it, that might be a hint as to how to attack a problem. Anybody know one of my favorite websites? It's 4 letters. Yes, OEIS. Right? The Online Encyclopedia of Integer Sequences. Okay, you can put in a sequence of numbers and it will tell you all of the places it knows where this sequence of integers has arisen. And it will tell you things about these numbers. Here are some properties, here are some relations, here are some references. And so if you can just calculate a few terms, if you have an idea of where they might be coming from, that can help guide you into a proof. So as soon as I see 2n minus 1 double factorial, I think about how many ways can I match things in pairs. This is going to be very useful when we do random matrix theory, when we're trying to calculate moments, and I'm trying to look at how many ways can I match things. If I have to match things in pairs and I have 2n objects, the maximum number of matchings is 2n minus 1 double factorial. Not every matching may contribute. Okay. The next part is calculating the moments of the semicircle distribution. And so it's been normalized so that x goes between -1 and 1. So we want to find the moments. What can you tell me about the odd moments? 0. So I just have to integrate from -1 to 1 of x to the 2m 2 over pi square root of 1 minus x squared dx. Any thoughts as to what might be a good way to do this integration? Yeah, trig substitution, right? Would you have gotten that if I hadn't been in trig substitution? Why should you be thinking trig substitution? You've got a 1 minus x squared. Do you want x to be sine or cosine? It doesn't matter, but I think there's a natural choice. And if you want, you could also say that this is equal to twice the integral from 0 to 1 of x to the 2m 2 over pi square root of 1 minus x squared dx. So I think it's more natural to do sine or cosine. Which do you think? Why?
Because 1 minus sine squared is cosine, and you have an integral, and the integral of cosine is sine, and the integral of sine is negative cosine.
There's that, but there's a more natural reason why I would probably choose sine. What's the range for x?
12 and 4.
X goes from 0 to 1,
Oh,
right? If I choose cosine, so I would probably say, let's let x be sine of theta. And so now theta is going to go from 0 to pi halves. Does it really make a difference? No. And so we're going to get 4 over pi integral theta goes from 0 to pi halves. And now we'll have, x is going to be sine of theta to the 2m. So sine of theta to the 2m. 1 minus x squared is 1 minus sine squared, which is 1 minus, which is cosine squared squared becomes cosine of theta. Now you can see why I want to go from 0 to 1, because I don't have to worry about cosine being negative. Now, if x is sine of theta, dx is going to be cosine theta d theta. So this actually becomes a cosine squared of theta d theta. Okay. Who wants to integrate sine to the 2m cosine squared? Doesn't seem pleasant, does it? Any thoughts as to how you might attack this?
cosine theta is sine theta.
You could do this in terms of exponential functions, but that's going to make it a little bit painful because you're going to have to raise things to powers. Complex analysis might be able to help you, but you're integrating over a line segment. What techniques do you know? Remember, if all you have is a hammer, every problem looks like a nail. What integration techniques do you know? Integration by parts. Do you know partial fractions? Yeah. Doesn't look like partial fractions. So if we want to integrate by parts, I need a u and a dv. U should somehow involve sine to a huge power because I want to try to lower things. And dv, how might you try to do things? So my first thought might be to try to have u involve sine to a high power. But maybe that's not the best thing. Maybe it's better to have the sine with the dv. Because what would sine of theta to the 2m love to have tagging along with it? Yeah, what if I tried sine of theta to the 2m cosine theta d theta, and I let u be cosine theta? Is v easy to do? So what would I get for v? So sine theta to the 2m plus 1 over 2m plus 1. And what would du be? Minus sine of theta d theta. So if we call this mu sub 2m, we get mu sub 2m is 4 over pi, and then the integral is going to be uv minus v du, right? So we're going to have sine of theta to the 2m plus 1 cosine theta over 2m plus 1 at 0 and pi halves. Minus and a minus becomes a plus. The integral from 0 to pi halves of v du. So we're going to have a sine of theta to the 2m plus 2 over 2m plus 1 d theta. Yes? What's the boundary term going to be? Zero. So we get mu of 2m is 1 over 2m plus 1, integral from 0 to pi halves, 4 over, I guess I had 4 over pi outside before, and then we have sine of theta to the 2m plus 2. That's the sine of theta to the 2m times sine squared. But what's sine squared? One minus cosine squared of theta. So if we save this, move to the next page, we have the following relationship, and this is equal to 4 over pi, integral from 0 to pi halves, and then we had, I think, sine to the 2m theta cosine squared of theta d theta. That's what we started with, right? So notice this is looking pretty similar. So we get mu 2m is 1 over 2m plus 1, 4 over pi, integral from 0 to pi halves, sine of theta to the 2m d theta, minus 4 over pi, integral from 0 to pi halves, sine of theta to the 2m cosine squared theta d theta. What does the second integral equal? It's just mu 2m. So we have a 1 over 2m plus 1. So when we subtract, we get 2m over 2m plus 1, mu of 2m is equal to 4 over pi, integral from 0 to pi halves, sine to the 2m theta d theta. So the question is, can we do that integral? How? You really like exponential today. And again, it's...
I promise it's going to be very easy.
So I'm not saying exponential is a bad way to do it. And so if you do exponentials, you're integrating from 0 to pi halves.
Because then it's going to be like e to the I theta minus e to the negative I theta.
So the question is the only term that's going to survive essentially a constant term?
Yeah.
So there's several ways. So we will do exponential. I will do exponential. Could we do anything to the integral of sine 2m theta?
Oh.
Yeah, how should I write sine 2m theta? This is the same as sine to what power? 2m minus 2 theta times 1 minus cosine squared of theta. So this would give you 4 over pi, integral from 0 to pi halves of sine 2m minus 2 of theta d theta minus 4 over pi integral from 0 to pi halves sine of 2m minus 2 cosine squared of theta d theta. That's mu of 2m minus 2. So one way to do this is actually we can start to see a recurrence relation. And as we do this, we're going to just keep getting higher and higher powers of sine that we need to evaluate. So this is one way to attack the problem. So another way is we want to do this integral. And so we can use the fact that sine of theta is e to the I theta minus e to the minus I theta over 2. So 2i, sorry, 2i. You know what they say about complex analysis? It's only fun till someone loses an eye. Peter Jones taught me that when I was an undergraduate. So sine of theta to the 2m, we'll have 1 over 2i to the 2m. And then we'll have e to the I theta minus e to the minus I theta to the 2m. And then we want to integrate this from 0 to pi halves.
Well, it's probably better to first square or just expand it.
Well, so the question is, which terms are going to matter? So one thing I could do is I could pull out either an e to the I theta or an e to the minus I theta. Let's pull out an e to the I theta. So this is the sine of theta to the 2m. This is a 2 to the minus 2m. 1 over I, it's the same as negative I to the 2m. And we'll fix that next time. The negative to the 2m is just going to be 1, so we'll have an I to the 2. So that's just going to be negative 1 to the m. And then we pull out, we'll have e to the 2m I theta, 1 minus e to the minus 2I theta to the 2m. And so now sine of theta to the 2m is 2 to the minus 2m. Negative 1 to the 2m is 1. I squared is minus 1, so this is going to be minus 1 to the m. E to the 2m I theta. And now we'll have a sum, k goes from 0 to 2m, of 2m choose k. And I'll just do it as negative 1 to the k, e to the negative 2I k theta. And then it'll be 1 to the 2m minus k. So then we get the sine of theta to the 2m is 2 to the negative 2m, negative 1 to the m. Now we'll have the sum, k goes from 0 to 2m choose k. We'll have a negative 1 to the k. We'll have e to the, did I put in an extra 2? Oh, no, there's a 2. Okay, so e to the, okay, good, to the 2m minus 2k I theta, right? And now if we integrate from 0 to pi halves of both sides, everybody agree I can forget about the 4 over pi for now? So that's 2 to the minus 2m, negative 1 to the m. Can I interchange the integral and the sum? Why? It's finite. Yeah, we actually don't have to justify it too painfully. It's a finite sum. So negative 1 to the k, 2m, yes, thank you. And now we have the integral from 0 to pi halves of this. And this, I can write this as cosine 2m minus 2k theta plus I sine 2m minus 2k of theta d theta. So I'm integrating cosine of an even number from 0 to 2m, from 0 to pi halves. What should I get? So when I integrate a cosine, I'm going to get a sine. I double where I evaluate things. I'm going to be evaluating at 0 and pi. What will I get? So I'll get 0. What about when I integrate the sine term? I'll then get cosine and what should I get? So when I integrate from 0 to pi halves, that's going to be evaluating the cosines at 0 and pi. Is that going to contribute or not contribute? I'm sorry. It looks like that's going to contribute. The other thing is you did the cosine integral wrong. The cosine integrals don't always vanish. When do they not vanish?
Wouldn't it just be easier to integrate into the minus 2k pi theta just because like the integral of that is going to be 1 over 2m minus 2k I to the.
But they're not all going to vanish.
Yeah, and then we're going to evaluate it.
Right. It's just complex analysis is not a prereq for this class. And so we technically don't know how to integrate. And that's why I'm writing it as your cosine plus a sine term. But do we agree that there's going to be some contributions here?
Right.
There's also one case you have to be careful about here when k equals m. Because when k equals m, you're going to get just 1.
Well, I guess we don't care about the I terms, right? Because the left-hand side is a real integral.
Good. So if you now make that observation that the left-hand side is real, then we know that everything has to be nice. And so we don't have, oh, I dropped the coefficients. I dropped the 2m choose k. So now if you note left-hand side is real, so on right-hand side, the signs cancel. Just get the k equals m. And then that will give you the integral from 0 to pi halves of sine 2m theta d theta is going to be 2 to the minus 2m, negative 1 to the m, negative 1, k equals m is just m, then 2m choose m. And now we're integrating 1 from 0 to pi halves. It's just going to be pi halves. So we can evaluate the integral. So it was some work. And you had to be clever. So this was the key observation. If you don't observe that, you're going to have something painful to play with. And so it all comes down to what is the best way to write the algebra to get everything to work. You know, one possibility is, would it be better if rather than going from 0 to pi halves, we went from minus pi halves to pi halves? But then things cancel nicer at this point. Because we could extend the integral from, instead of 0 to pi halves, from minus pi halves to pi halves, and then just divide by 2. And that just might make some of the substitutions a little bit nicer. I wanted to go from 0 to pi halves because technically when you're using the change of variable formula, you need a one-to-one function, or a function that's one-to-one almost everywhere. Some of the polar functions, they break down at the origin. Spherical coordinates, polar coordinates, they break down at the origin. Not a big deal. But we don't want, a 2-to-1 valued function. So this would allow us to figure out what these moments are. And we can go through now, and we now have it. And you can begin to see, I think, the Catalan numbers emerging. We've got the 2m choose m, and we had a 2m over m, 2m plus 1 or something like that earlier. The Catalan numbers are going to arise. So I'm not going to finish doing all the details there. It's also in the notes. Over here, we're also beginning to see a recurrence relation coming into play. If we can calculate these integrals of high powers of sine, and we can keep doing this by induction. And so we can try to find, formulas for the integrals of high powers of sine and get recurrence relations for that. So again, I'm not giving you all that much homework to do. If you're interested, try to see what is necessary to clean this up. But there's enough pieces here, and this is one of the things you want to get to the point where you can say, if I really cared, I know enough that I could make this work. I don't care. But I see the broad brushstrokes. I see how you would make it rigorous. There's no missing pieces. There's no key insights that are left. At this point, it's just mop up. Not necessarily pleasant mop up. And there could be easy opportunities to make algebra mistakes. But I don't need any more insights. Over here, we needed the insight of the left-hand side is real, so the imaginary term doesn't matter. So whatever that integral is, it's gone. Okay, so this gives us the moments of the semicircle. And it turns out these are the Catalan numbers. So I'm not going to finish the calculations, but it turns out when the dust settles, you get the Catalan numbers. You could, of course, go back and try to do the integral directly. Right? And integrate from, right? It is possible to do this. You might be able to play some games, change variables, make this into like a beta distribution. You've got a square root, so that makes it difficult. So no, I just had beta on my mind because I was doing then probability.
Because the beta distribution is like 1 minus x times 1 plus x. And then so this is like beta 1 half.
Right. And so if you play games like that, except it's, you normally do the exponent is b minus 1. And so, so I think there's ways you would have to change variables. You would have to let like u equal x squared. So as an aside, the beta distribution is, it's for x greater than or equal to 0, it's like t to the a minus 1, 1 minus t to the b minus 1. And I think it's gamma a plus b over gamma a, gamma b as the normalization constant. And then for x less than or equal to 0, it's 0. And so we had something like x to the 2m, 1 minus x squared to the 1/2. If you let u equal x squared, then du is 2x dx, or dx is equal to 1/2 x to the minus 1/2, which is u to the minus 1/2 du. So then this is going to become something like x to the 2m. It's going to become like u to the m, 1 minus u to the 1/2, 1/2 u to the minus 1/2. So it's going to look like a u to the m plus 1/2 minus 1/2, the 1/2 over here, and then a 1 minus u to the 1 minus 1/2, I think. I'm sorry. I want to have something minus 1. So it's going to be, I think, 3/2 minus 1. So it might be something like a beta with a equals m plus 1/2 and b equals 3/2. something like that. And then you're going to get ratios of gamma factors. But ratios of gamma factors, gamma of n plus 1 is n factorial if n is a positive integer. And then gamma of 1/2 is the square root of pi. So you might be able to just, do all this and make it work. So I think there's enough ingredients here that you could make the beta distribution argument fly. How many of you have seen the beta distribution? All right, so a lot of you have seen the beta distribution. If you have, try to make this work. There's more than one way to do things, which is great. And so we have an integral to do. It's not a pleasant integral to do, but it's an important integral to do. It's the moments of the semicircle. Okay, and now we need to show that the odd moments vanish in the limit. We've got about 9 minutes left. So the question is always, what do we want to do? I'm going to skip ahead a little bit. Hopefully this is visible. So years ago, I made these notes with some students where we looked at how many ways can you match things in pairs. And so if I have 3 objects, if I have 6 objects that I want to match in pairs, I've got to have 3 pairs. And so in the first one, boom, boom, boom. That's one way to do it. Another way is I could match these 2, and I could have a crossing for my matching. So I'm imagining that I have 2 endpoints on a circle, and I have to match them in pairs. And so if you look at it, there's 5 ways to do it. 1, 2, 3, 4, 5, where there are no multiple matchings. If you look at the other ones over here, you should notice that these 4 are all red. One way to view that is these 2 are matched, and these 2 are matched, and these 2 are matched, and these 2 are matched. So when I'm matching things in pairs, 2 of the pairs could actually be the same, and that would give you a quadruple matching. And so it turns out from a random matrix theory perspective, these aren't going to have to be worried about. We only care about where things are matched in pairs, and distinct pairs have distinct values. But since we were doing the calculation, we just wrote down all the different configurations and we kept track. If you look really closely, you'll see numbers like 3, 6, 1, 3, and 2. Any guesses what those numbers are? It's how many, it's basically symmetries. So if you look about this one, this is the easiest. Everything is matched with its opposite. There's only one way to do this. For this one, you have something matched with its opposite, and then the others are matched with their neighbors. How many ways can you match one thing with its opposite? There's 3 ways, and that's why this is a factor of 3. For the next one, you have a crossing and something matched with its adjacent. How many ways can you have something matched with its adjacent? There's 6 ways. And over here, you have the opposites, and that's why it's going to be 3 again. So those numbers tell you how many ways each of those configurations can arise. And then, we did, here, this was the 6th moments. This is looking at all the ways we could match 6 objects in at least pairs. What do you think the next one is? 8. And then just, continuing, all the different possibilities, where you start to have lots of things being matched in pairs. And, the final one is, everything is matched together. And so there's lots of configurations to think about. As you get to higher and higher moments, it gets worse and worse and worse. So one of the nice things about doing things like this is I should be able to just go back to earlier slides. And so we didn't do that yet. No, so okay, we haven't done that yet. Okay, so we didn't do. the density of states. Or did we? So this is Catalan numbers. No, okay. And then this is, yeah, okay. So we now need to do the odd moments. And so, did we do a lecture on the semicircle earlier in the semester or no? We have not. Okay. So how many of you have seen the Dirac delta functional? So this is a strange beast. So if I take the Dirac delta functional and I hit it with some function f of x, and I integrate from minus infinity to infinity, it returns the value of the function at a, if f is nice. Think of it as a unit point mass with all of the mass at a. A better way of looking at it is it's the limit as, say, maybe I give you, let's call it dn of x is 1 over the square root of 2 pi, I'll fix it in a moment, e to the negative x squared over 2, 1 over n squared, 1 over n. So this would be a normal with standard deviation 1 over n. Oh, so this should be squared over here. So as n gets larger and larger and larger, it's getting tighter and tighter and tighter. But I'm doing it in such a way that I have a nice function at any point. And if you look at something like that, and so we'll go into more detail on this on Thursday, imagine I give you something that's getting tighter and tighter and tighter, normally distributed. And then I give you some nice function f of x. And here, this is shooting up to infinity at the origin. What you would like to do is basically say, look, if I integrate delta n of x times f of x dx, do you agree that this is basically integrating from minus epsilon to epsilon of delta n of x, f of x dx? Because as it shoots higher and higher and higher up, as long as f is nice, it doesn't really matter the value away from the origin. But near the origin, what's true if f is a nice function? What's the value of f of x? It's almost f of 0. So this is basically just f of 0 times the integral from minus epsilon to epsilon. And since this is a Gaussian, this equals 1. So this is just a rigorous way to attack problems. So I thought we had seen this before. Since we haven't, I'll add some slides for Thursday and just talk about where this comes from. So the idea is we're going to form a way to get our hands on the eigenvalues of matrices. And to calculate them, we're going to have to calculate averages of polynomials involving the matrix elements. Polynomials involving matrix elements, it turns out it's going to matter how we match things. Well, a lot of what we were doing today was talking about matching things. The Gaussian, its moments tell us about how many ways can we match things in pairs. Everything is going to come down to matching things in pairs. And so all of the stuff we're doing is going to now come together and play out. And you're going to see that the Gaussian is going to be an upper bound for just how bad things can be, for what's the maximum contribution. The semicircle is much, much smaller. The Gaussian has unbounded support. The semicircle has very bounded support, just lives between -1 and 1. So we'll see on Thursday that the only things that matter are when things are matched in pairs where you don't have any crossings. And that's why all of these pictures here is, and you can try to figure these out for yourself. How many ways can I match things in pairs with crossings, without crossings? With nothing, no pair being allowed to be matched with another pair. And so, for instance, over here, this is all distinct pairs. This is every pair is the same. All right, so this is a good place to stop. Again, a lot of the stuff today is meant to just give you a sense of, if you wanted to do the calculation, you should now have enough knowledge to do it. It is up to you if you want to do the calculation.